Alright, this is the notes for section 2 of chapter 2. This is on proving theorems. Most of these are going to be proven indirectly, so instead of just manipulating the left-hand side of the equation, it's going to be manipulating a third equation, and the third equation can be used to prove the first and the second are equal. And this is going to be over the ways that addition and multiplication behave in an ordered field. The first one is going to be the cancellation laws. Cancellation. So this is kind of like the thing we have A plus B equals C plus B if and only if A equals C. And this is kind of like what you did in grade school, where you'd have A equals C, and you want to manipulate the equation, you add the same thing to both sides. Or if you have A plus B equals C plus B, you do inverse operations and subtract B from both sides. And so proving this, you have to prove two different statements, because you have to prove the first one right here, and you also have to prove the second one, because if and only if is two statements. So we will start off proving this one. It's easier in my opinion. A equals C, then A plus B equals C plus B, and we'll call this the left arrow proof. So the left arrow proof would be this right over here, because it's going from over here to over here. And we'll start with our statements and our reasons to chart. And our first statement, instead of starting off by saying A equals C, we're going to start off with a statement that kind of looks like our end goal in a way. So we'll start off with A plus B equals A plus B, which we know is true from the reflexive property. And so we're looking at this like, yeah, that's true, but there's not even a C in this equation. We're not starting on the left side. We have to introduce the C. And so then we can introduce the A equals C as a given. And now that the A equals C as a given, now anywhere we see an A, we can substitute a C in. So now we can say A plus B equals C plus B, because we substitute the A for a C. And so now, all of a sudden, starting out something that wasn't either of the two equations, we popped out our end goal. And so QED. And now we'll prove over here, we'll prove the initial way. So if we have A plus B equals C plus B, then A equals C. So we have the A plus B equals C plus B, and we'll just use this as our given. This will be our first statement. And so this one is proven just straight off the left-hand side. Then we have A plus B plus negative B equals C plus B plus negative B. Oh, that's not a space. I'll rewrite that. And this, we're just using this cancellation law that we established going from the right to the left. So our justification is going this way in the equation, because we showed that add anything to both sides is still an equal statement. Now we associate negative b equals c plus b plus negative b. And then since addition it is associative. And then we got a plus 0 equals c plus 0. That's the add inverse. And then a equals c, add identity. And then we just get our QED. And now we've shown that you can add, if you add or subtract the same thing in addition, the same is the same. And off of that, you have a few corollaries that you can do. I won't prove them here, but they can be proved using the cancellation laws. The key corollary here is that this, which looks surprisingly similar to this thing that we learned earlier, the sets, where this equals itself, inverse of the inverse equals the original statement, and then we use cancellation laws for multiplication. For cancellation multiplication, it's the same thing as before, but b doesn't equal 0 because then you get the nasty multiplying and dividing by 0, or dividing by 0, which doesn't go well. And so this is AB equals CB if and only if A equals C. This is the same thing as earlier, but instead of addition, adding things from both sides, subtracting things from both sides, you're multiplying, dividing things from both sides. So here we have AB equals AB. This is similar. This is going to be extremely similar to the method we just used. A equals C, AB equals CB, and we'll say reflexive given sub QED. And then going the opposite way. We want to prove given A equals, or AB equals CB, then A equals C. We'll do AB equals CB, that's our given. AB 1 over B equals CB times 1 over B, and that's going to be using what we learned over here. You can multiply the same thing by on both sides and it works. We got A times B times 1 over B equals C times B times 1 over B. This is the full multiplication dissociative. You got A1 equals C1 from the inverse, then A equals C from the multiplicative identity. And that's QED. So this is almost 100% identical, you're just using a different operation. If you noticed that in both these proofs I kind of used a weird notation. Instead of subtracting or dividing, I added a negative or multiplied by a reciprocal. That's because I haven't yet introduced the definition of subtraction and division. And so the definition of subtraction is that you have A minus B equals A plus negative B, and A divided by B equals A times 1 over B. This is actually relatively useful notationally. You just don't think about it that often. So now that we have these introduced, then we can write the things out. But we still have to keep in mind that when we are adding or multiplying both sides by the same thing, because we have the cancellation law for addition, we have the cancellation law for multiplication. We do not have those for subtraction and division, because instead of subtracting something from both sides, you're actually adding inverse or you're multiplying by the inverse, which can trip you up a little bit. It's not that big of a deal, but technically you have to add or multiply. And then there's a few more rules for multiplication. I'll prove one of them. So we have a times 0 equals 0. We have 1 over a equals a. And we have negative a equals negative 1 times a. So these are three things that you learn really early. These two especially, you just never even thought, oh, I need to prove these because they come very intuitively. This one maybe isn't as immediately intuitive, but if you rewrite it as 1 divided by 1 over a, 1 over 1 divided by 1 over a, 1 times a over 1 from your 5th grade math class, then you see, oh yeah, it makes sense pretty intuitively. But you still have to be able to prove these as true statements before you can use them. I'll prove probably negative a equals negative 1 times a, because I think, actually, I think it's pretty intuitive. Actually, no, I'll do times 0 because that's probably the one most people think is the most intuitive. And so, we'll start off, instead of using like the left hand side, we'll go off of a times 0 equals a times 0 plus 0, which you're looking at this, you're like, yeah, makes sense. You have to justify it though. These are both the additive identity, so this is true because 0 plus 0 equals 0. Then you gotta do this really janky step where you freaking distribute the a over the 0 plus 0. And this is left distribution. You're looking at this like, well, yeah, but it's just not a very nice thing looking at all these a times 0, so it gets kind of awkward. But, let's see. Well, yeah. You can 0. Oops. Yeah, you add 0 to the left side. And that's just that, to the additive identity. And now, you see, since we now that we have two things over here instead of just this one thing that we can group or not, doesn't really matter since they're both one single statement. Now we have 2 on both sides. Now we can subtract things from both sides. So we'll subtract a times 0 from both sides. 0 equals a times 0. And so we use the cancellation law of addition. Because we subtracted the a times 0 from this side, got the 0, a times 0 plus a times 0 over here. But since we're trying to find that a times 0 equals 0, this isn't 100% correct yet. We have to rewrite it as a times 0 equals 0 and use the fact that get the symmetrical law of quality. Looking to see if there's any other thing. I don't think I'm gonna prove anything else. I'll also just introduce 2 other slightly more complex, not more complex. One of them's actually really, really simple, but one of them's really complex. Well, relatively complex. The other was relatively simple. So that's 1 over AC equals 1 over A times 1 over C. And then the other one, the simple one, is x equals y, then negative x equals negative y. This one should be really easy for you to prove by yourself, and this one, if you want to challenge yourself, you can prove this one. Alrighty, I think that's it for this chapter.